In this third and final installment, we're going to take a look at a completely coupled system. So as you might guess, this is where a rate of change is dependent on both dependent variables. If we're talking about a system of two dependent variables, then each differential equation is dependent on the values of the other differential equation. So suppose the contaminant from our previous lake flows in lake 1 is blocked off. So we don't have an inflow from a foreign source, but the water from lake 2 loops back into lake 1, and C1 of 0 equals 5,000, C2 of 0 equals 0. So essentially what we're saying is we have this system of two lakes. We have lake 1, and then we have lake 2, and I'm just sort of going to draw this kind of willy-nilly here, but this one's output goes into lake 2. So this is lake 1, and this is lake 2, and then the lake 2 also loops back into lake 1. So basically we have, you can kind of imagine this as sort of a cycle, and lake 1 has an initial concentration of this contaminant of 5,000 grams, whereas the second lake has no initial content. So the idea is, hopefully, that we can see here is eventually these are going to cycle back and forth, and this 5,000 is going to become distributed between these two lakes. So if we start to model this, the rate of change going in C1 is dependent on what's coming in. But what's coming in is a function of what's going out of lake 2. Okay, so we're assuming the same, we have the same rate of water, 100 gallons per day coming into lake 2. So 100 gallons per day. And we need to multiply that by the number of milligrams per gallon, or grams per gallon, which is C1 divided by how many gallons there are, which is 50,000. And then coming out of lake 2 is a rate of 100 gallons of water per day, multiplied by the number of grams per gallon, which is C2 per 60,000 gallons. And therefore, we can see that what comes into lake 1 is 100 C2 over 60,000. And then what exits lake 1 is 100 C1 over 50,000. And if we further look at that for lake 2, we'll really just notice that it's the same terms, just inverted signs, because they're looping back and forth. So this is a problem because realistically we can't solve the first equation until we solve the second equation and plug it into the first, but we can't do that until we solve the first equation. So we have sort of a loop here that it seems infinite and seems like a catch-22. But the strategy, if we're going to use Laplace transforms, is to solve it as a system of equations. So first of all, we'll solve the first equation for the Laplace of C1, substitute, find C2, then substitute back into the original equation. Now I'm warning you, this gets pretty messy, but it can be done with just some careful attention. So first of all, I take the Laplace of the first equation, which we recall is this guy here, and I'm going to reduce it. Of course, I'm going to cancel out my two zeros. My 100 can cancel out with 100 there, and my 100 there can cancel out with 100 there, and so on and so forth to make this a lot simpler. So I will have the Laplace of dc1 dt is s Laplace of c1 minus c1 at 0 equals 1/600th Laplace of c2 minus 1/500th Laplace of c1. Now you notice that we have two dependent variables here. So c2 and c1 are both functions of time, and therefore there's nothing you can do further beyond just calling it Laplace of c2 and Laplace of c1. So what we're going to do here is we're going to isolate Laplace of c1 like we normally would, except we're going to avoid the inversion step. So c1 of 0 is 5,000, and so we add that to this side, and then we have our c2 over here. So we're going to isolate c1, and the way we're going to do that is we're just going to say Laplace of c1 equals this term divided by s plus 1 over 500, this term divided by s plus 1 over 500. And now we Laplace the second equation and substitute this line right here in place of Laplace of c1. We'll plug in this here. So you'll see what we'll do in a second. So there's our second equation. There's our next line similar to the first. There is our substitution step. So this looks really, really messy right now. But basically what we've done here is we have taken the Laplace of c1, which is which is this expression. So all I've done is I've replaced Laplace of C1 with this junk right here. So it's going to look really scary for a minute. So that's that substitution right there. I'm going to do some arithmetic here to clean this up. So I'll distribute my 1/500th to the first and second terms, which leaves me with 1/500th times 1/600th is 1/300,000th over s plus 1/500th. And I'm just writing that as a multiple of Laplace of C2 plus 5,000 divided by 500 is 10 over s plus 1/500th minus the third term. Okay, here's the tip that will make this a little bit cleaner is clear the denominators because we have fractions on top of fractions and it just gets kind of hideous. So we'll multiply through both sides by s plus 1 over 500. Now you have to be careful when you do this to watch your algebra because we're multiplying both sides in their entirety by this. So every single term needs to get multiplied by this, this factor. So that means I'll multiply it over here. So I have s plus 1 over 500 times s times Laplace of C2. And that takes care of, cancels that guy out right there. So I just end up with just that portion. That cancels out, so I just have plus 10 minus 1/600th times. Again, that needs to multiply all three terms, here, here, and here. And so I get that right there. So remember, now we've got everything in terms of C2. So this becomes just a standard Laplace transform problem now because you notice that my only dependent variable in this equation is C2. So what I'm going to do is I'm going to now proceed as usual. So, whoops. 1 sec. Okay, so what I'm going to do now is, let's see what happened from the past step. Oh, nothing, that's just a carryover of that last step here. So there's that last step. So what I'm going to do is move all the C2s over. So I'll have this original term minus this term plus this term, so it's a subtraction sign, equals 10. So I'm leaving 10 on that side. Now I'll factor a Laplace of C2 out, and I've got this big extraneous mess. But here's where it was helpful to clear the denominators, because now what I'm going to do is, for the first time ever, we are going to clean up all of this stuff. We're going to combine like terms. And if we do that, we see that these two terms cancel, leaving us just with an s squared and two s terms. And if we figure out how to add these fractions here, you could put it in decimal form if you really want to, but it ends up, you can use a calculator and convert it back to fraction when you add them, 11/3000 s. So this is cleaned up quite nicely. So I'm going to divide both sides by s squared plus 11/3000 s. So I've done that here. So it's just 10 over that portion. And then that equals, so now I'm going to factor out an s because that's going to allow me to see that now this is a partial fraction decomposition. So I'll have 10 over this b minus a. A is 0, so I have 10 over 11/3000 times the first factor minus the second factor, and then I just did a little bit of manipulation of the fraction, 30,000 elevenths times that, and now I can invert this. So C2 of t equals, well, the inverse of that is just 1, so I have 30,000 elevenths times 1, minus that, which is 30,000 elevenths e to the negative 11/3000 t, so remember that's an exponential form, and so that's my solution for C2. Okay, well, we're getting close. Things don't get quite very clean here, but we're going to go back now to the first Laplace equation and substitute in LC2. So remember, we had this at one point. The Laplace of C1 equals this whole mess. And so we also know that the Laplace of C2 equals this quantity here. So my goal is now that, now that's, keep in mind, that's not my solution, that's the line before my solution, that's this thing here. And I'm going back to the first Laplace equation, and in this equation, I'm now going to substitute out what the Laplace of C2 is equal to. Well, the Laplace of C2 is equal to this thing. This was prior to inverting it. And when I plug that big old mess in, so all I've done here is I've replaced L of C2, that quantity, with this whole mess right there. Looks very scary, but let's take our time. We're going to multiply through by the fraction. And I say take our time, but I didn't really take our time. So these two fractions produce 50 elevenths. And because we're taking, so this is just a constant, we have a fraction minus a fraction, so we're dividing both fractions by this guy, which means this s plus 1/500 will go into this denominator, which forms s times s plus 1/500, minus 50/11, that's distributing now to this term, s plus 11/3000, and that gets divided by s plus 1/500. And then there's my third term. Okay, almost there. So I'm going to do my partial fraction on the first term, that's this guy here, minus the partial fraction on this term, that's this guy here, plus the third term, that's this guy here. And finally, I'm just going to do a little bit of inverting. So clean up this fraction, comes out to 25,011ths. And the inverse of that is 1, so 25,011ths times 1, minus 25,011ths times the inverse of that, which is e to the negative 1/500th t. That nasty fraction product right there becomes 30,011ths. And the inverse of that is e to the negative 11/3000ths t. Yeah, so that's a positive factor right there because I have a negative 1 over b minus a comes out to negative 1 over negative 1/600th. And then I'll distribute that to this guy as well, and the inverse of that is e to the negative 1/500th t. And then I have plus 5,000 e to the negative 1/500th t. Now, here's where things get really pretty because all of these three terms, if you look at these coefficients of the e to the negative 1/500th t term and the coefficient there, those are both negative, and that's positive, and these three add to 0. So if you add those up, they add to 0, which just leaves me with this term, which is that guy. That leaves me with the negative 11/3000ths t term, which is that guy, and those are my only two terms in that solution. Finally, we're done after 12 minutes of talking through that. So to sum things up, here was our model, and our solution was these two equations right here. So very interesting. Let's check it out. Let's go over to Desmos and see what's happening. In Desmos, we graph these two, and we can see that one of them started up at, this is obviously Lake 1, started with 5,000 grams, and progressively started to taper off. In fact, as the limit of this guy as x approaches infinity is 25,011ths. So basically this converges down to 25,011ths, which is about 2272.729. And this one converges because this term decays to 0, but because we're subtracting off a decaying term, it actually gradually rises to 30,011ths, which is that amount. So it's kind of interesting that Lake 1 dropped well below where it started, and not only that, but it dropped well below Lake 2. Well, why are the amounts different? Well, the amounts are different, but if I take 25,011ths, which is the number of grams in the long run in Lake 1, and I divide it by the volume of the water, 50,000, notice how I get a concentration of about 0.05 grams per gallon. So again, this is in the long run, that's how many grams I expect. The gallons of water is not changing. Now I'll do the same thing for the other one. Now the other one has more water, so I'd probably expect it to have, if there might be equal concentrations, that one's going to reach about 27.27 grams in that lake, but that's out of or inside 60,000 gallons of water. And we can see that in the long run, even though the amounts are different, the grams per gallon of water end up being exactly the same. So again, keep in mind that our model, we had these two lakes circulating back and forth. So ultimately, all that water is going to become totally mixed in with the contaminant, whatever that might be. So really interesting problem dynamics. Now, of course, as you've noticed, this process was less than desirable. That was a lot of work. And the thing to really keep in mind here is this is considered to be a pretty simple system. Not simple to solve, but it's simple in terms of the assumptions. We're assuming a closed system between two lakes. We don't have any extraneous flows. We don't have any complicated dynamics, and the solution became very difficult to find. So imagine how quickly this becomes practically impossible. So from a practical perspective, quickly becomes impossible. So that's it for the video. Hopefully this has been helpful, and enjoy those Laplace transforms.